On a clear night, you lean back and see a sky of stars. Your brain accepts at once that there are many lights up there, far too many to count. Yet if someone froze the sky and asked you to count each one, you would give up very quickly. Human minds were built for small numbers, not for oceans of stars. In this journey, we will push that ancient brain into a universe of ridiculous quantities and watch where intuition fails. If you enjoy calm, deep dives into the cosmos, please like this video, subscribe to the channel, and come with us as we try to count the uncountable. Start small. Picture 3 bright stones on a table in front of you. You take one quick look, and you know there are 3 without thinking about it. Add a 4th, and it still feels effortless. This instant recognition of tiny quantities has a name in psychology, but you do not need the term to feel how it works. Your brain is doing something like a visual snap judgment, a built-in counter for very small groups. Now imagine 8 stones scattered on that same table. You glance once, and most of the time you cannot say the exact number. You hesitate, your eyes dart, and you start to group them, maybe 4 and 4 or 5 and 3. Past about 4 objects, the brain stops giving crisp numbers and switches to estimation. It can sense that 8 is more than 4 and that 12 is more than 8. Yet the feeling becomes fuzzy. Put 2 crowds side by side and you can often tell which is larger, but ask for the exact counts and the certainty disappears. This is where counting comes in. Humans invented number words and counting systems to stretch beyond that built-in limit. 1, 2, 3, 4, 5, and so on, each word a little mental step. With counting, you can handle 10 stones, or 50, or 100. You can tally the number of people at a concert or the number of books on a shelf. It still takes time, but it remains possible, at least on paper. The problem is that our sense of meaning does not keep up. Think about the difference between 10 and 100. It feels big, almost dramatic. The difference between 100 and 1000 already feels less sharp. Between 1000 and 10,000, your brain may just shrug and call both of them many. Somewhere along the way, the emotional weight of the number stops rising in step with the digits you write down. To see how quickly this blows up, imagine counting steadily out loud, one number every second. Reaching 1000 would take a bit more than 16 minutes. Reaching 1 million would mean counting day and night for nearly 2 weeks without sleep. Reaching 1 billion would take more than 30 years of non-stop counting. Reaching 1 trillion at that pace would take over 30,000 years, longer than all of recorded human history. At that point, the words 1 trillion are easier to say than the time it would actually cost you. Yet compared with the cosmos, even a trillion is still a small warm-up. Your home galaxy, the Milky Way, probably contains hundreds of billions of stars. Surrounding it are many other galaxies, each with their own floods of stars. The total number of stars in the part of the universe we can see is not just larger than a trillion. It is a number so large that writing it out in full would fill a line with zeros and leave your number sense lying on the floor. Here is the quiet problem. Every time we talk about how many stars there are in the universe, we reach for number words that our brains were never designed to feel. We can write them on a screen, but our inner picture remains fuzzy and vague, the same way 8 stones blurred together on that table. Before we even start a serious cosmic star count, we are hauling around a mine that crashes very early. So in the next parts of this journey, we will do something strange. We will keep using this flawed human intuition, but we will also learn how astronomers carefully work around it. We will climb step by step from a single star in your night sky to a rough count of all the stars in the observable universe. Along the way, you may notice your gut feelings protest, stumble, and sometimes catch up. That tension between what feels true and what the numbers tell us is where the real story begins. When you walk outside on a clear night, it feels like the sky is full. Your eyes drift from constellation to constellation, and the darkness between the stars seems thin, as if it is only there to frame the lights. It is easy to believe that you are seeing a representative sample of what is really out there. The sky looks crowded, and your brain quietly concludes that the universe must be crowded too. Yet almost everything you can see with your naked eyes belongs to a very small neighborhood in one single galaxy, and even that galaxy hides most of its stars from you. Under truly dark skies, away from city lights, a healthy human eye can pick out a few thousand stars, not millions, not hundreds of thousands. At any one time, from one place on Earth, you might see 2,000 or 3,000 individual stars. If you could somehow visit every point on Earth and add up all the stars visible from all those different horizons, you might reach something like 6,000 distinct stars in total. That is the entire naked eye star catalogue of the human species, spread across the whole planet. Most people today never get close to that number. In a city washed by streetlights and billboards, the night sky collapses into a few stubborn points, maybe a handful of bright stars and 1 or 2 planets hanging over the glow. Even in better conditions, haze, humidity, and the height of the observer will change the count. Yet the pattern never changes in one crucial way. Almost every star you can see without a telescope is one of our near neighbours inside the Milky Way. The wider universe does not show up on its own. There is one big exception that ancient sky watchers knew well. Across the sky, on clear dark nights, runs a pale band, a milky river of light. It is not made of mist or cloud. Look closely, and you can sense that it is made of too many tiny lights to separate. This band is the disk of our galaxy seen from inside it. You're sitting in a flat system of stars and gas. When you look along the plane of that disk, your view crosses through billions of distant stars that blur into a soft glow. When you look away from the disk, toward the top or bottom of the galaxy, the sky thins out. Astronomers now describe the Milky Way as a barred spiral galaxy. That means that at its centre, there is a bar-shaped structure of stars, and from the ends of that bar, spiral arms curl outward through space. The whole system is a kind of cosmic disk, thick in the middle and thinner near the edges, with a halo of old stars and dark matter surrounding it. Our Sun does not live in the middle. It sits roughly halfway between the centre and the edge of the disk, in a smaller structure often called a spur between 2 major spiral arms. From that position inside the disk, the night sky becomes easier to understand. When you look along the disk, you're looking through a long cross-section full of stars. They pile up along your line of sight, making the Milky Way band bright and crowded. When you look up or down, away from that plane, you're looking out of the thin side of the disk, so you see fewer stars and more empty space. The structure of our galaxy quietly shapes every night sky image you have ever seen, even if you had no name for it. Even with nothing but their eyes, early astronomers sensed that the sky had limits. More than 2,000 years ago, observers in the Mediterranean world made lists of stars and gave them places and names. Hipparchus, and later Ptolemy, compiled catalogues with a few hundred bright stars marked by position and brightness. They could not add more because their eyes and the light of their world would not allow it. Still, these early maps were the first attempts to move from the feeling of a crowded sky to an actual count of what could be seen. Centuries later, in Europe and other parts of the world, astronomers with better instruments made larger catalogues. Telescopes began to resolve fainter stars, and suddenly regions that once held only darkness now shimmered with new points. In the 18th and 19th centuries, observers started to notice fuzzy patches that were not stars at all. Some of these were clusters inside our own galaxy. Some were distant galaxies whose true nature would only be revealed much later. Even as the counts grew, the pattern held. Almost everything that was easy to see belonged to our local island of light. Here is the quiet twist. The Milky Way likely holds something like a few 100 billion stars. Your naked eyes pick out a few thousand. If the entire galaxy were shrunk down to the size of Earth, the stars you can see unaided would be like a few houses lit up in a single town, while the rest of the continents, oceans and cities stayed dark to you. The night sky feels rich because your brain is sensitive to contrast and pattern, not because it is sampling the true richness of the galaxy. Every time you stand under the stars, you're really standing inside a system that almost never shows itself directly. Dust clouds in the disk hide huge regions from visible light. The dense core of the galaxy is buried in gas, dust and blinding starlight that your eyes cannot separate. Beyond that, the outer halo and the many faint dwarf companions around the Milky Way remain invisible to ordinary vision. The sky that feels full is in fact pared down, filtered and strictly local. Yet that limited view is the starting point for everything that follows. From a few thousand naked eye stars, humans learn to recognize the Milky Way band, to suspect that we live inside a flattened swarm of stars, and finally to measure its rough size and structure. The story of counting the stars does not begin with the whole universe. It begins with this one galaxy, and with what that pale band across the sky quietly reveals. In the next step, we will see how astronomers estimate the total number of stars in the Milky Way without leaving home, and how even that task stretches our methods to their limits. Imagine standing in a dense forest and trying to work out how many trees exist in the entire woods. You can see some trunks nearby. The more you walk, the more you realize there are hills, clearings, patches of thicker growth. Counting every tree one by one would be hopeless. Yet with a bit of sampling and a rough map of the land, you might still estimate the total number fairly well. That is exactly the position astronomers are in with the Milky Way. We live inside the forest. We see only some of the trees, and yet we want a number for all the stars. The first step is to understand our local patch of space. Around the Sun, within a sphere stretching a few dozen light years in all directions, we know the stars comparatively well. Over the past century, careful surveys have mapped almost every star brighter than a certain limit in this neighbourhood. Missions in space have measured their distances and motions with exquisite precision. This tiny bubble around the Sun is our deepest sample, the place where we can count fairly honestly and say, here is how crowded space feels in one pocket of the galaxy. What we find is both surprising and underwhelming. Space, even inside a galaxy, is very empty. Within 10 light years of the Sun, there are only a few dozen stars. Within a cube of space, 1 light year on a side, the odds of finding more than one star are small. The Sun is not in the middle of an overwhelming swarm. It is more like a house in a sparse rural landscape. Still, this sparse neighbourhood gives us a number, an average density of stars per unit volume of space, at least for this part of the Milky Way. Now imagine placing that local density into a rough blueprint of the galaxy. Astronomers model the Milky Way as a flattened disk with a certain radius and thickness. They add a bulge in the centre, like the raised centre of a fried egg, plus a faint halo of stars reaching far above and below the disk. Each of these components has a different typical density. The core is packed, the disk is thinner, the halo is very diffuse. By combining the local measurement with other lines of evidence, such as how bright the disk appears from the inside and how star counts change as you look closer to the centre, astronomers can sketch how the density falls off with distance. At that point, the problem becomes one of math. Take the density of stars in each region, multiply by the volume of that region, add everything up, and you get an estimate of the total number of stars. The answer lands somewhere in the range of a few hundred billion. Some studies lean closer to 100 billion, others suggest 200 or even 400 billion. The differences reflect how uncertain we still are about the galaxy's exact shape, thickness, and the true mix of bright and faint stars in different zones. We have a ballpark, not an exact ticket count. There is a second major route to the same goal, one that looks not at individual stars but at the total light. A galaxy is a glowing object in space. If you can measure how much light it emits in different colours, you can infer how much stellar mass must be there to produce that light. The key concept here is called mass to light. In plain terms, it asks, for each unit of light we see, how many units of star mass are required? That ratio is not constant. Young galaxies full of hot blue stars shine very brightly for their mass. Old galaxies dominated by small red stars shine more dimly for the same total mass. To use this method in the Milky Way, astronomers compare the detailed mix of stars in our neighbourhood with the light they produce. That gives a local relationship between brightness and mass. Then they measure the total light of the Milky Way as seen from outside, using observations of other similar edge-on spiral galaxies and indirect measurements. By combining the two, they estimate the total mass in stars that must exist in our galaxy. Finally, they divide by the typical mass of a star. Because most stars are small, this gives a fairly large number of stars, again of order a few hundred billion. To make sense of this, we need to talk about stellar populations. Not all stars in the Milky Way are the same age, composition, or brightness. There are young, metal-rich stars in the spiral arms, forming from gas enriched by earlier generations of supernova explosions. There are older, metal-poor stars in the halo and bulge, relics of the galaxy's youth. The distribution of star masses, sometimes called the stellar mass function, is heavily tilted toward low-mass stars. For every bright blue giant that burns out quickly, there are many small red dwarfs that sip their fuel and shine faintly for trillions of years. This imbalance creates a kind of cosmic illusion. Most of the light comes from the minority of bright stars. Most of the stars are faint, small and almost invisible at large distances. When we look toward the center of the galaxy, we see the combined glow of many bright stars and assume that region carries a huge fraction of the stellar population. In reality, countless faint stars spread throughout the disk can dominate the count. Any attempt to estimate star numbers from galaxy light must therefore correct for this hidden majority. A third line of reasoning comes from gravity itself. Stars orbit the center of the Milky Way, and their speeds depend on how much mass lies inside their orbits. By measuring those orbital speeds at many distances, astronomers can build a rotation curve for the galaxy. From this, they infer how much mass is needed to keep stars from flying off into space. Most of that mass turns out to be invisible dark matter, but some of it is in stars and gas. By subtracting estimates of gas mass and modelling the dark matter halo, you are left with an estimate of stellar mass, which again leads to a total star count. The strange beauty of this situation is that all three methods point to roughly the same story. Whether you start from local density, from total light, or from the pull of gravity, you end up with a Milky Way that holds on the order of a few 100 billion stars. Yet the methods do not agree perfectly. They differ by tens of billions here and there. Each carries its own assumptions, corrections, and blind spots. Together they form a network of cross-checks, a way of making sure we are not fooling ourselves too badly. So when you hear that the Milky Way contains, for example, about 200 billion stars, understand what that sentence really means. It is a careful estimate built on small samples, models of structure, guesses about the mix of bright and faint stars, and the measured motions of countless suns. It is not a head count. It is our best attempt to describe a forest from deep inside the trees. The uncertainty is not a flaw. It is the natural result of asking an enormous question with finite tools. Once we accept that even our own galaxy comes with error bars, the next leap becomes both daring and natural. If we can estimate the stars in this one island of light, perhaps we can estimate the stars in all galaxies we can see. In the next part, we will step beyond the Milky Way, follow the trail of faint smudges that once confused early observers, and learn how we discovered that the universe is filled with many more such islands, each with their own hidden forests of stars. For most of human history, the Milky Way was not one galaxy among many. It was the universe. The bright band across the sky, plus the scattered stars around it, seemed to be all there was. Beyond that glowing arch lay darkness and stories, not other islands of light. Even when telescopes arrived and revealed more and more detail, they did not immediately reveal the true scale of the cosmos. They added confusion first, and only later clarity. When early observers turned their new glass eyes to the sky, they saw something strange. In addition to sharp pinpoints of starlight, there were fuzzy patches that refused to resolve into single stars. Some looked like smudges. Some had spiral shapes. These were called nebulae, a word that simply meant clouds. No one knew for sure what they were. Were they gas clouds inside the Milky Way where new stars might be forming? Or were they entire systems of stars so far away that they blurred into a faint haze? Through the 1800s, astronomers catalogued these nebulae one by one. Some turned out to be star clusters within our galaxy. Some really were gas clouds glowing under the light of nearby stars. Others remained mysterious. A few, like the faint patch in the constellation Andromeda, were bright enough to see even without a telescope from very dark sites. That particular smudge became one of the most important objects in the history of astronomy, but for a long time it was just one entry among many in lists of puzzling clouds. By the early 1900s, astronomers had made detailed maps of the Milky Way. Many believed that the entire universe was a single flattened disk of stars with the sun near the centre. The spiral nebulae were thought to be swirling gas within that disk. Others suspected that some of those spirals might actually be island universes, separate star systems comparable to the Milky Way itself, lying at enormous distances. The debate became known as the Great Debate for a reason. It was not only about nebulae, it was about the size of everything. The argument could not be settled by appearance alone. A spiral shape on the sky does not tell you how far away an object is. To break the deadlock, astronomers needed a kind of standard candle, a class of star whose true brightness could be known from some other property. If you know how bright a star really is, and you measure how bright it appears, You can work out how far away it must be. Distant objects look dimmer. The relationship is simple even if the universe that uses it is not. Enter a particular kind of star that changes its brightness over time. These stars pulse, growing brighter and dimmer on a regular schedule. Early in the 20th century, the astronomer Henrietta Leavitt, working at Harvard College Observatory, studied such stars in nearby clusters and in the small Magellanic Cloud, a small companion galaxy to the Milky Way. She discovered a pattern. The longer the period of the star's pulsing, the brighter it truly was. This link between period and intrinsic brightness turned those pulsing stars into powerful distance markers. A little more than a decade later, Edwin Hubble used a large telescope on a mountain in California to examine the Andromeda Nebula in detail. Inside that soft cloud of light, he identified individual pulsing stars of the same type Leavitt had studied. By measuring their periods, he could infer how bright they truly were. By comparing that to how faint they appeared, he could calculate the distance to Andromeda. The result was shocking. Andromeda lay far outside the expected size of the Milky Way. It was not a nearby cloud. It was a separate galaxy made of stars. With that one measurement, the universe grew. The Milky Way was no longer the entire cosmos. It was one island of hundreds of billions of stars floating in a far larger sea, and Andromeda was another island of similar size. Other spiral nebulae now fell into place as galaxies as well. The fuzzy smudges that had puzzled observers for generations turned into distant cities of stars. The phrase, island universe, once a bold idea, became the new normal. From there, astronomers began to classify galaxies the way earlier naturalists had classified plants and animals. Some galaxies are graceful spirals with sweeping arms of stars and gas curling out from a bright center. Some are smooth ellipticals, shaped more like eggs or spheres, with little structure visible and populations of older stars. Some are irregular, twisted by past encounters or by bursts of star formation. Sizes range from tiny dwarf galaxies with a few million stars to giant ellipticals with perhaps 1 trillion stars or more. Each galaxy type carries clues about its history. Spirals tend to have ongoing star formation in their arms, fueled by gas that has not yet been used up. Ellipticals often hold older, redder stars and less cold gas, suggesting a more violent past with mergers and collisions that scrambled their disks. Dwarf galaxies are easily tugged and distorted by larger neighbours, and many such dwarfs swarm around big galaxies like the Milky Way and Andromeda. The sky that once seemed to hold only one great system now holds a rich ecosystem of many. The emotional shift is easy to miss because the story is often told as historical fact, a debate, a measurement, a realization. But imagine what it meant at the time. In the span of a few decades, the human sense of home went from a single disk of stars to one of countless galaxies scattered through space. Every bright spiral seen through a telescope became a separate realm with its own history, its own star birth and star death, its own chance for planets, and maybe for life. The night sky stopped being a ceiling and started to look like a vast city seen from far away, each light a different building, each building packed with rooms. For our question about star numbers, this change is crucial. Before the discovery of external galaxies, asking how many stars exist was effectively asking how many stars are in the Milky Way. After the discovery, the same question became much larger. Now we needed not only an estimate for the stars in one galaxy, but an estimate for how many galaxies there are and how many stars each one holds on average. The problem of counting the forest expanded from one stand of trees to a whole continent of forests. We now stand in a universe where these island galaxies are everywhere. The next step is to learn how we count them. Surprisingly, we do not map every galaxy across the sky one by one. Instead, we take some of the deepest, narrowest looks in the history of astronomy and try to build a cosmic census from those tiny keyholes. In the next part, we will stare into one such keyhole and see how a pinhead-sized patch of sky can tell us about hundreds of billions of galaxies and the overwhelming number of stars they contain. Imagine choosing a spot in the night sky that looks completely empty. No bright stars, no obvious clouds, nothing. Now imagine pointing one of the most powerful telescopes ever built at that tiny patch and letting it stare for days. Most of us would expect very little to come back. After all, it looked blank. What came back instead was one of the most important photographs in the history of science, and the foundation for our best estimate of how many galaxies, and therefore how many stars, fill the observable universe. The patch chosen for that first famous deep stare by the Hubble Space Telescope was astonishingly small. If you held a grain of sand at arm's length, the area of sky it covered would be larger than the region Hubble studied. Over many days, the telescope gathered light from that speck of darkness, building up a picture photon by photon. The result, called the Hubble Deep Field, did not show an empty sky. It showed a field crowded with thousands of tiny, colourful shapes. Almost every one of those shapes was a distant galaxy. Some of the galaxies in that image look like familiar spirals and ellipticals. Others are stretched, clumpy, or oddly shaped, the marks of collisions and of a younger universe where galaxy building was still messy. Many of them are incredibly far away. Their light left them billions of years ago when the universe was young and only arrived at Hubble after crossing most of cosmic history. That single picture is not just a snapshot of distance. It is a slice of time, a line of sight through billions of years. Once you know roughly how many galaxies appear in that tiny speck of sky, a simple but bold idea suggests itself. The sky is a sphere around Earth. If you know how many galaxies lie in one small patch of that sphere, you can multiply by how many such patches would tile the entire dome of the sky. This is like counting trees in a small, randomly chosen square of forest, and then multiplying by how many such squares fit into the whole woodland. It gives a first estimate of how many galaxies might exist in the observable universe. The first deep field was only the beginning. Astronomers repeated the experiment in other directions, with longer exposures and improved instruments. The Hubble Ultra Deep Field stared at an even smaller region and went deeper, revealing around 10,000 galaxies in a patch of sky that would fit behind the head of a pin held at arm's length. Later refinements produced what is often called the Hubble Extreme Deep Field, combining many observations over many years to reach even fainter objects. Each new deep image reinforced the same basic message. The universe is packed with galaxies in every direction. Even in places that look empty to your eyes, there are countless systems too faint and too far to register without long exposures. When astronomers extrapolated from these deep fields to the full sky, early estimates suggested that the observable universe might contain on the order of a few trillion galaxies. That number alone is staggering, especially when you remember that many galaxies host hundreds of billions of stars. Over time, though, the picture became more nuanced. As surveys improved and more detailed modelling of galaxy populations was done, some of the early galaxy counts were revised downward. Better understanding of how galaxies merge, how many faint systems exist, and how telescope sensitivity affects detection led to newer estimates closer to a few 100 billion galaxies in the observable universe rather than trillions. The exact number is still debated, and in a sense it will always be a moving target as new instruments come online. Into this story stepped the James Webb Space Telescope, with its powerful infrared eyes designed to see even farther back in time and through clouds of cosmic dust. Webb's early deep fields pushed the view of the universe to new extremes, revealing very young galaxies that formed only a few 100 million years after the Big Bang. Some of these galaxies appear surprisingly bright and massive for such early times, raising questions about how quickly structures formed. Each new deep field both sharpens and complicates the cosmic census. The method behind all of this remains conceptually simple, even if the details are intricate. Choose a patch of sky. Count how many galaxies you can detect in that area down to a certain brightness. Correct, as best you can, for those that are probably there but too faint to see. Repeat in several directions to avoid any one region that happens to be unusually dense or unusually sparse. Then scale up to the whole sky. Add in knowledge about how galaxy brightness relates to star numbers, and you have a way to turn galaxy counts into rough star counts. Of course, the universe is not perfectly uniform. Galaxies clump into filaments and walls, leaving great voids where there are fewer systems. Deep fields sample only narrow cones through this structure. There is always a risk that a particular line of sight passes through an unusually busy corridor or an unusually empty gap. To reduce that risk, astronomers take multiple deep fields in widely separated parts of the sky and combine them. They also compare deep field results with wide but shallower surveys that cover large areas with shorter exposures, trading depth for breadth. Even with these precautions, the uncertainties are real. We cannot see the faintest galaxies directly. We can only infer their numbers from patterns in the ones we do see, and from models of how galaxies grow over time. The fraction of stars that live in dwarfs too dim to show up in most surveys is still being debated. Yet the overall picture remains robust. Whether the number of galaxies in the observable universe is a few hundred billion or somewhat more, the scale is clear. We live in a cosmos where galaxies are as common on the sky as grains of dust on a floor. For our purposes, the key point is this: from tiny patches of sky, from images that could fit behind a grain of sand, we have built a cosmic census that spans the observable universe. When you hear a headline saying that there are hundreds of billions of galaxies, that claim rests on these deep, patient stares into apparently empty space, each patch is a keyhole. Through enough keyholes, a picture of the whole cathedral emerges. In the next part, we will step back from how many galaxies there are to the distances involved. After all, counting galaxies is only half the story. To turn their light into star numbers, we need to know how far away they are. That requires a ladder of methods stretching from nearby stars to the edge of the observable universe, each rung resting on the one below it. To turn galaxy counts into star counts, we need more than sharp images. We need to know how far away those galaxies really are. A galaxy that looks faint might be small and nearby, or huge and very far away. Without distance, brightness tells us almost nothing. So astronomers have spent more than a century building a strange tool that exists only in their minds and in their data, a layered structure of methods called the cosmic distance ladder. Each rung of this ladder reaches farther than the last, and each depends on the one below. The first rung is as down to Earth as it gets. It is geometry. When Earth orbits the Sun, our viewpoint shifts by about 200 million kilometers from one side of the orbit to the other. Nearby stars appear to wobble slightly against the more distant background as our vantage point moves. This tiny back and forth motion is called parallax. By measuring how much a star shifts over 6 months, and knowing the size of Earth's orbit, astronomers can use simple triangles to calculate the star's distance. For a long time, parallax could only be measured for a handful of very nearby stars. The angles involved are incredibly small, often smaller than 1,000th of a degree. Early ground-based telescopes struggled against the shimmering of Earth's atmosphere. In the late 20th century, space missions like Hipparcos, and later the Gaia Space Observatory, changed the game. Free from atmospheric blur, they measured parallaxes for millions and then more than 1 billion stars with exquisite precision. This gave us a solid map of distances in our local region of the Milky Way. Parallax is pure and satisfying, but it does not reach very far. Beyond a certain range, even the best instruments cannot detect the tiny shifts. To go farther, astronomers needed a way to turn certain stars into standard candles, objects whose true brightness could be known. The idea is simple. If you know how bright a candle really is, and you see how faint it appears from your house, you can work out how far away it stands in the dark. In space, some stars cooperate with this plan. One of the most important examples is the family of pulsing stars first studied in detail by Henrietta Leavitt. These stars grow brighter and dimmer in a steady rhythm. Leavitt discovered that there is a tight link between the period of that rhythm and the star's true luminosity. Longer period means truly brighter. Once that relation is calibrated using parallax distances for nearby examples, astronomers can look at a pulsing star in another part of the galaxy, or in a nearby galaxy, and read off its distance from the timing of its heartbeat. This is how Edwin Hubble measured the distance to the Andromeda Galaxy, and showed that it lay far outside the Milky Way. But the method did not stop there. Pulsing stars have been used to map the structure of our galaxy, to measure distances to many nearby galaxies, and to refine the scale of the universe. They form the second rung of the ladder, resting on parallax and supporting more distant work. The stronger the calibration at the bottom, the better the distances at the top. Beyond the range where pulsing stars can easily be seen, another kind of standard candle takes over. Certain white dwarf stars in binary systems can steal matter from their companions until they reach a critical mass and explode in a runaway fusion event. These explosions, a particular class of stellar outburst, reach nearly the same peak brightness each time. When one goes off in a distant galaxy, it briefly shines with a recognizable intensity. By comparing that known peak brightness to how bright it appears to us, Astronomers can judge the distance to the host galaxy, even across hundreds of millions or billions of light years. These stellar beacons made it possible to measure how fast the universe is expanding. By combining distance estimates with measurements of how much the light from a galaxy is stretched to the red, astronomers found that more distant galaxies are moving away faster. The relation between redshift and distance is another rung on the ladder. Redshift itself is not a distance measure. It is a proxy for how much space has stretched while light was travelling. To turn that into actual numbers, you need those earlier standard candles tying specific redshifts to specific distances. Step by step, the ladder builds a chain that reaches from the Sun to nearby stars, to star clusters, to neighbouring galaxies, and finally to the deep universe. At the farthest extremes, distances are inferred not from individual stars at all, but from the overall patterns of galaxy clustering and delicate ripples frozen into the glow from the early universe. Those patterns encode a standard scale, a kind of background yardstick. Matching that yardstick to the nearer distance measures lets astronomers stitch the whole cosmic map together. It is tempting to imagine this ladder as a solid construction, like a tower of steel. In reality, it is more like a carefully balanced stack of books. Any error in the lower layers ripples upward. If parallax measurements are off by a small fraction, then the calibration of pulsing stars is slightly wrong. That in turn skews the distances to nearby galaxies, which shifts the inferred brightness of exploding stars, which then alters the estimated distances to far galaxies and the measured rate of cosmic expansion. Every step carries uncertainty, and each uncertainty multiplies along the chain. For our question about how many stars exist in the observable universe, this matters deeply. The number of stars we infer from galaxy surveys depends on both how many galaxies we count and how far away they are. Distance affects volume. A small fractional change in the assumed size of the observable region translates into a big change in how many galaxies and stars it contains. The cosmic distance ladder is not just a side topic. It is part of the foundation under every grand headline number you hear about the universe. Yet there is a quiet triumph here as well. Over the past century, improved instruments and clever methods have tightened the rungs of the ladder again and again. Parallax measurements have become more precise. The behaviour of standard candles has been mapped in finer detail. Independent checks, using different kinds of objects and patterns, now cross-verify the scale. We still argue about small differences, but the broad structure holds. We have gone from guessing rough distances to nearby stars to measuring distances across most of the observable universe with surprising confidence. In the next part of this journey, we will step sideways. Instead of climbing farther, we will walk around inside a typical galaxy and look closely at how its stars are distributed. To turn galaxy light into star numbers, we need to know what lives inside a galaxy, how many small faint stars hide behind each bright one, and how that mix changes from one type of galaxy to another. Only then can we start multiplying galaxy numbers by stars per galaxy and approach a total star count for the cosmos. When you look at a galaxy photo, it is easy to imagine it as a flat picture, a pretty swirl on a screen. The bright core, the curving arms, the faint outer haze all feel like paint on black canvas. Inside that picture, though, are hundreds of billions of individual suns, each with its own orbit and history. If you could fly through a galaxy, it would not feel like a smooth glowing disk. It would feel more like a vast, thin city of scattered streetlights, full of districts that look nothing alike. Start near the core of a spiral galaxy. The centre shines as a bright, dense bulge. Stars here are packed far more closely than in our neighbourhood. Their orbits loop around the galactic centre in tangled paths, sometimes tilted, sometimes elongated. Many of these stars are old. Their light tends to be yellow or red, the colour of suns that have burned steadily for billions of years. Deep in the very heart, a supermassive black hole lurks, its gravity shaping the motions of the inner region. But most stars there are too far from it to notice directly. Move out from the bulge into the disk, and the scenery changes. The stellar crowd thins. You begin to see the spiral pattern from within. The arms are not solid bands of stars. They are regions where gas and dust pile up, and where stars are more likely to be forming. Young hot stars light up these areas in bluish tones. They burn fast and bright, carving bubbles in the gas around them with their intense radiation and fierce winds. Many of them will explode as supernovae after only a few million years. Between the spiral arms lies what might be called the quieter suburbs of the galaxy. There are still stars everywhere, but fewer raw nurseries. Most stars here are of modest mass. Many are small, cool red dwarfs that shine dimly and steadily for times longer than the current age of the universe. These little stars dominate by number. If you could make a list of all the stars in a galaxy, the vast majority would be these faint, long-lived embers. Yet when you look at the galaxy from far away, they barely show up. Astronomers capture this idea in something called the stellar mass function, a description of how many stars exist at each mass. In plain language, it says that as you go to lower masses, you find more and more stars until eventually the numbers level off. High-mass stars are rare. Medium-mass stars like the Sun are more common. Low-mass red dwarfs are everywhere. This skewed distribution means that most of the light you see from a galaxy is produced by a small luminous elite, while most of the stars by count live in the shadows. Dust adds another layer of complexity. The disks of spiral galaxies are laced with dark lanes, wisps and bands that cut across the bright background. Those are clouds of tiny solid particles mixed with gas. Dust grains block and scatter starlight, especially at shorter wavelengths, making regions behind them look dimmer and redder. From our position inside the Milky Way, dust clouds in the disk hide entire swaths of the galaxy from view. Even when we observe other galaxies from outside, dust can veil their inner workings. To count stars, we must correct for this cosmic smog. Gas is the raw material from which new stars form. In spiral arms and other active regions, gas clouds collapse under their own gravity, fragmenting into clumps that will become stars and clusters. This process never fills all the gas at once. It is patchy and influenced by past generations of stars. Supernova shocks can compress gas and trigger new star formation in some places, while powerful winds and radiation can blow gas away in others, shutting the process down. A snapshot of a galaxy captures this dynamic interplay frozen at one moment in time. Different galaxy types arrange these ingredients in different proportions. A dwarf irregular galaxy might have a modest number of stars but large reservoirs of gas, with scattered pockets of intense star formation. A giant spiral like the Milky Way has a substantial disk, prominent arms, a central bulge, and a mix of young and old populations. A massive elliptical galaxy has little cold gas, almost no obvious dust lanes, and a smooth distribution of mostly older stars. Its light is dominated by redder tones, and its star formation rate has often dwindled to almost nothing. To turn this messy internal structure into a star count, astronomers use models that link the total light of a galaxy to its stellar mass. These models assume a shape for the stellar mass function and track how the population ages over time. Young galaxies full of massive blue stars shine very brightly for their mass. As those stars die and leave behind less luminous remnants, the galaxy's light per unit mass drops. By comparing observed colours and brightness to these models, astronomers estimate how much stellar mass must be present, and thus how many individual stars there are. Here the uneasy feeling creeps in. We cannot see most of the stars individually, especially in distant galaxies. We see blended light filtered through dust, altered by distance, and mixed from regions with very different histories. We assume that the stellar mass function is similar in many places, that the share of faint red dwarfs to bright giants does not change wildly from one galaxy to another. We know this is not exactly true, yet it seems to be true enough for rough work. The models are tested against nearby galaxies where we can resolve more stars, then applied farther out. Every choice in these models adds uncertainty. Change the assumed fraction of low-mass stars and the inferred number of stars in a galaxy shifts. Change the average age of the stellar population and the relation between light and mass slides. Even the way dust is distributed can alter the apparent colours and thus the estimated mass. Astronomers cope with this by comparing multiple models and by using different wavelengths of light, from ultraviolet to infrared, to pierce dust and better separate young and old stars. Despite all these complications, a pattern emerges. Dwarf galaxies can host anything from a few million to a few billion stars. Milky Way-sized spirals typically hold on the order of a few hundred billion. Giant ellipticals at the centres of clusters can contain up to 1 trillion stars or more. When we speak of an average galaxy having a certain number of stars, We are really averaging across this wide range, weighted by how common each type is. There is no single typical galaxy, yet the concept is useful when we step back to cosmic scales. So when you see an image of a galaxy, try to imagine it from the inside. Think of the old crowded bulge, the younger spiral arms, the quiet outer disk, the faint halo of ancient stars and invisible dark matter wrapping around it all. Think of the tiny red dwarfs that make up the silent majority, and the hot blue giants that briefly shout their presence before dying. Each galaxy is a layered, living system, not a flat pattern. Our estimates of how many stars it holds are really estimates of how many such lives are present inside that structure. In the next part, we will zoom even farther out, to the level where galaxies gather into clusters, filaments, and walls. Stars are not spread evenly through space. They live in these tangled structures, leaving vast volumes almost empty. To understand the total number of stars in the observable universe, we must understand not only the contents of a single galaxy, but where galaxies themselves prefer to live in the grand architecture of the cosmos. If you could step far outside the Milky Way and keep going, past nearby galaxies and even past galaxy clusters, the universe would start to look very strange. At first, it might seem like a loose cloud of galaxies scattered in all directions. Look longer and patterns emerge. Galaxies are not sprinkled evenly like sugar in water. They gather in threads and knots, leaving great regions almost empty. On the largest scales we can map, the universe looks like a three-dimensional web, and almost every star that has ever existed lives somewhere along its strands. To see this web, astronomers had to do something that sounds simple and is actually very hard. They had to measure the positions of hundreds of thousands and then millions of galaxies in 3 dimensions. A photograph gives only directions on the sky. To add depth, you need distances, which usually come from the redshift of a galaxy, that gentle stretching of its light as the universe expands. When you combine sky positions with redshifts for many galaxies, you can build a 3-dimensional map of where they sit in space. Large galaxy surveys have done exactly that. Telescopes on Earth have slowly scanned wide swaths of the sky, taking spectra of one galaxy after another, measuring their redshifts and placing them in a cosmic coordinate system. When the data are plotted, the result is breathtaking. Galaxies line up in long filaments that stretch across hundreds of millions of light years. At the intersections of these filaments sit massive clusters, crowded knots where thousands of galaxies share the same neighborhood. Between the filaments and clusters lie vast voids, regions so underpopulated that you might pass through tens of millions of light years without meeting a single bright galaxy. This pattern has a history. In the early universe, matter was almost but not quite evenly spread. Tiny differences in density, seeded by quantum fluctuations in the very young cosmos, began to grow under the pull of gravity. Regions slightly denser than average attracted more matter, becoming denser still. Regions slightly emptier were drained over time. Dark matter, which interacts mainly through gravity, formed a scaffolding of clumps and threads. Ordinary matter, the kind that forms stars, fell into this framework, lighting up where the dark matter was thickest. On smaller scales, inside a filament, galaxies feel each other's gravity and gather into groups and clusters. A group might contain a handful of large galaxies and several dwarf companions. Our own local group with the Milky Way, Andromeda, and dozens of smaller galaxies is one example. Clusters are the city centers of the cosmic web, with hundreds or thousands of bright galaxies embedded in massive halos of dark matter and hot gas. Between these hubs, filaments act like intergalactic highways, along which galaxies slowly drift and merge. Star density follows this architecture. Most stars in the universe live inside galaxies, and most galaxies lie in the filaments and nodes of the web. The voids contain relatively few galaxies, and therefore relatively few stars. If you were to choose random points in space and ask whether each point lay near a star, almost all the yes answers would cluster along the web, while the vast volumes of the voids would nearly always yield silence. In a statistical sense, the universe is both incredibly full and incredibly empty at the same time. This clumpy structure matters for our star count because it shapes how we sample the universe. A deep field image that happens to look down a filament rich in galaxies will suggest a higher average density than one that passes mostly through a void. Wide surveys smooth over these differences, but only if they cover enough sky and enough depth. When astronomers estimate the number of galaxies per unit volume, they must correct for the fact that they live in a particular spot that may not be completely typical. Our own location is an example. The Milky Way and Andromeda sit in a modest group that in turn lies on the edge of a larger concentration of galaxies sometimes called the Laniakea supercluster. This region is part of a broader flow of matter, slowly falling toward even denser zones. On heroic scales, galaxies and clusters move along the filaments like leaves drifting down cosmic rivers. The large-scale map is still being refined, and new surveys continue to reveal deeper connections between structures that once seemed separate. From the point of view of a single star, all of this may seem irrelevant. A sun in the outskirts of a small galaxy does not feel the full drama of the web. Its life is determined mainly by local conditions in its host galaxy. Yet from the point of view of cosmic accounting, the web sets the stage. It decides where galaxies form easily and where they do not. It governs how often galaxies collide and merge, events that can trigger bursts of star formation or quench it entirely. Regions near the dense nodes of the web tend to host massive clusters and giant galaxies stuffed with stars. The quiet interiors of voids host fewer and smaller systems. Simulations that follow the growth of structure from the early universe to the present day help make sense of this. They start with a nearly uniform mix of dark matter and gas, sprinkle in tiny initial ripples, and then let gravity and simple physics run. The result, when compared to real galaxy surveys, is strikingly similar. A web of filaments, nodes, and voids emerges, with galaxies lighting up along the densest strands. From these simulations, we can estimate how much matter ends up in galaxies, how much remains in diffuse gas, and roughly how that stellar mass is distributed across different environments. When we combine all these insights, a picture emerges. The observable universe contains a certain average number of galaxies per unit volume, but that average hides a wild range. Clusters at the nodes of the web might contain hundreds of trillions of stars packed into a region a few tens of millions of light-years across. Voids of similar or larger size may hold only a few small galaxies with a few billion stars each. On the larger scales, the contrasts cancel out and we can talk about a meaningful average star density. But we always know that reality is lumpy. So the question, where do stars prefer to live, has a clear answer. They live where gravity has had time to gather matter into dense structures, along the filaments and in the nodes of the cosmic web. They avoid the vast empty voids not by choice, but because there was never enough material there to light many of them in the first place. When we quote a total number of stars in the observable universe, we are really summing over this tangled network of bright regions and dark gaps. In the next part, we will add one more dimension to this picture. We will let time flow. The cosmic web has not always looked like it does now, and the rate at which new stars turn on has changed dramatically over the history of the universe. To understand how many stars exist today, and how many may yet be born, we need to trace the rise and fall of star formation, from the first lights after the Big Bang to the slow fading of the far future. Up to now, we have treated stars and galaxies as if they simply exist, as if the universe were born with its present stock of suns already in place. In reality, stars have a history. They switched on gradually, surged into a long, bright afternoon, and are now drifting into a slow twilight that will last for unimaginably long times. To understand how many stars exist today, and how many may yet be born, we have to watch the universe live its life. We need to see when the cosmos was busy making stars and when it began to ease off. Roll the clock all the way back to the first few 100,000 years after the Big Bang. At that point, the universe was hot, dense, and filled with a smooth mix of hydrogen, helium, light, and dark matter. There were no stars yet, only tiny ripples in density. As the universe expanded and cooled, those ripples grew under gravity. Slightly denser pockets pulled matter inward. Over tens of millions of years, gas in those pockets began to collect into the first small halos that would one day host galaxies. Eventually, some of those gas clouds collapsed so far that their centers ignited nuclear fusion. The first stars were born. They were unlike most stars in the universe today, made almost entirely of hydrogen and helium, with practically no heavier elements. They could grow to enormous masses. Many of them may have been hundreds of times the mass of the Sun. That made them hot and extremely bright, but also short-lived. They burn through their fuel in only a few million years before collapsing into black holes or exploding and sprinkling heavier elements into space. This era of first light began a few 100 million years after the Big Bang. The radiation from the first stars started to change the universe around them, ionizing the surrounding gas and carving bubbles of hot, transparent plasma in the fog of neutral hydrogen. As more stars and early galaxies formed, these bubbles grew and merged. Over time, most of the hydrogen between galaxies became ionized again. The universe went from dark and foggy to lit and clearer. This whole transformation is sometimes called the cosmic dawn. It marked the beginning of large-scale star formation as we would recognize it. From that point, the star formation rate of the universe began to climb. Small galaxies merged to form larger ones. Gas fell along the filaments of the cosmic web into deepening gravitational wells. Wherever enough gas collected, stars began to form. For the first couple of billion years, the universe was learning how to make galaxies efficiently. Many newborn systems were chaotic, full of clumps and tails from recent collisions. Yet during this messy era, the overall rate at which new stars were being born kept increasing. Several billion years after the Big Bang, the cosmos reached what you might call its busy season. Observations of distant galaxies show that the global star formation rate peaked when the universe was roughly a quarter to a third of its current age. At that time, on average, galaxies were making new stars at a much higher rate than they do now. Gas was more abundant, galaxies were colliding and merging more often, and the gravitational wells in which they sat were still being filled. The night sky, if you could have seen it from a safe spot, would have been rich with blazing young stars and frequent stellar explosions. From that peak onward, the story is one of gradual decline. Gas, the raw fuel for star formation, is not infinite. Each generation of stars locks some of it into long-lived dwarfs, or into remnants like white dwarfs and neutron stars. Supernovae and stellar winds blow some gas completely out of galaxies into intergalactic space, where it becomes harder to gather again. Collisions between galaxies can briefly trigger new waves of starbirth, but they also tend to heat and stir the gas, making it more resistant to collapse. Step by step, the universe begins to run low on easily usable fuel. Today, more than 13 billion years after the Big Bang, the global rate of star formation is far lower than at its peak. Many large galaxies, especially giant ellipticals in rich clusters, have almost completely shut down new starbirth. They shine mainly with the light of old, long-lived stars. Others, like the Milky Way, continue to form stars at a modest pace in their disks. Dwarf galaxies still flicker with small bursts of activity. But the overall rhythm has slowed. The universe is not done making stars, yet it is past its most intense youth. When astronomers add up the history of star formation, they can estimate how many stars have already been born in the observable universe. The answer depends on how efficiently gas was turned into stars at different times, and how much gas remains. Roughly speaking, a large fraction of the stars that will ever exist may already have formed, but not all. The countless red dwarfs that dominate by number will keep shining for trillions of years. New stars will continue to appear in small numbers, especially in gas-rich dwarfs, and in the outskirts of galaxies where cold gas still pools. Far in the future, the rate of star formation will dwindle toward almost nothing. Most gas will have been used up, locked into faint stars or spread so thinly that it never collapses again. Galaxies will grow redder as blue giants vanish and only the longer-lived stars remain. The universe will slide into an extended age of red embers, a time when new suns are rare and most light comes from old, cooling stars. In that distant era, the total number of stars in the observable universe will have crept only a little higher than it is now. The main work of star building will already be behind it. This history matters for our sense of the star count because it shows that any number we quote today is a snapshot, not a final tally. There are stars that once existed and have already died, leaving no visible trace except in the elements scattered through space. There are stars that exist now and stars that will form in the future from gas that is still drifting in the dark. When we ask how many stars there are, we usually mean how many are shining at this moment in the observable universe. Yet behind that number lies a long story of rise and decline. In the next part, we will turn from stars themselves to what circles them. Over the past few decades, we have learned that planets are common, perhaps even more common than stars. If each of the hundreds of billions of galaxies in the universe holds countless stars, and each of those stars hosts its own family of worlds, then the star count is not just a measure of light. It is a rough measure of how many planetary systems, how many possible skies, and how many chances for life the universe may hold. For most of history, stars and planets were blended together in the human mind. A star was a point of light. A planet was a wandering point of light that moved differently. No one knew whether other stars had planets at all. The sun seemed special, a rare lantern with its own family of worlds. In the last few decades, that picture has shattered. We now know that planets are not rare decorations. They are a natural byproduct of star formation. Once you see that, the raw number of stars in the universe turns into something else in your mind. It turns into a rough count of possible worlds. The change began with careful watching. Astronomers looked at stars and noticed tiny, regular dips in their brightness. Not the dramatic flashing of a variable star, but a small, steady dimming that repeated on a fixed schedule. The best explanation was simple and powerful. A planet was passing in front of the star from our point of view, blocking a small fraction of its light. Each transit carved a shallow notch in the star's light curve. By tracking that pattern, astronomers could infer the planet's size and its orbital period. Other methods joined in. Some planets tugged on their stars strongly enough that the stars wobbled slightly as they orbited the common center of mass. That wobble shifted the star's spectrum toward red and blue in a regular rhythm. From that rhythm, astronomers could estimate the planet's mass and orbit. A few planets could even be imaged directly with clever techniques that blocked the star's glare. Piece by piece, a new picture emerged. Planets were everywhere, in a vast variety of sizes, orbits, and combinations. The numbers grew fast. Early discoveries were rare and celebrated one by one. Then dedicated missions stared at thousands of stars at once, looking for those tiny dips in brightness. They found hundreds, then thousands of planets. Many orbited stars not so different from the Sun. Many others circled smaller, cooler red dwarfs. Some planets hugged their stars in orbits of only a few days. Others took years to complete a circuit. The message was clear. If a star has a disk of gas and dust around it when it forms, planets are almost an automatic outcome. From these surveys, astronomers began to estimate occurrence rates. Instead of asking whether planets exist around other stars, they asked how often they appear. The answer was striking. On average, there seems to be at least one planet per star in our galaxy, and probably more. Many stars host multiple planets. Small rocky planets, not just giant gaseous worlds, turn out to be common. Even stars very different from the Sun can host complex systems, with compact chains of planets packed close in or wide families spread over large distances. Once you combine that picture with the estimated number of stars in the Milky Way, the raw count of planets becomes mind-bending. If our galaxy holds a few 100 billion stars, and there are on average at least as many planets as stars, then we are looking at hundreds of billions of planets in this one galaxy alone. Scale that up to hundreds of billions of galaxies in the observable universe, and the number of planets becomes so large that the mind can barely grasp it. Worlds are not scattered rarities. They are the default outcome. Among those planets, a small subset will orbit at distances where liquid water could exist on their surfaces, given the right atmosphere. This region is often called the habitable zone, a band around a star where the balance of heating and cooling might allow oceans and lakes. The exact boundaries depend on many factors, including the star's brightness and the planet's own properties, but the concept gives us a way to think about potentially life-friendly worlds. Surveys suggest that a noticeable fraction of stars, especially smaller red dwarfs, may host at least one planet in or near this zone. It is important to stay honest here. A planet in a habitable zone is not automatically habitable. It might lack an atmosphere. It might be tidally locked, with one side baked and the other frozen. It might be flooded with harmful radiation from a flaring star. On the other hand, life could arise in places our current picture would call hostile, such as deep oceans under ice or in subsurface seas. The point is not to count certain life-bearing planets. We are nowhere near that. The point is to show that the raw stage count is enormous. There are many places where interesting chemistry could unfold over long times. When we ask how many stars exist in the observable universe, we are therefore asking how many engines of planetary systems exist. Each star is a potential center of a family. Some families are small and sparse, others are busy and tightly packed. Some stable systems will last for billions of years without being disturbed. Others will be reshaped by close encounters, slow drifts, or violent interactions. The huge star count tells us that whatever the odds of complex life on any one world, the number of trials the universe runs is vast. This can be both comforting and humbling. On the one hand, it suggests that our own existence is not the result of a single impossible accident, but of a universe that tries many combinations. On the other hand, the same numbers remind us that even if life arises elsewhere, the distances between stars are so great that most civilizations, if they exist, may never know about each other. The universe offers countless possible skies and yet keeps them isolated by sheer scale. The star count speaks both of abundance and of separation. From a purely physical point of view, all these planets also matter for the future of stars. Planets can alter stellar rotation through tidal interactions. They can shepherd debris and comets, feeding occasional material back into the star or flinging it away. In dense environments, close encounters between systems can strip planets or swap them, adding one more layer of complexity to the story. Yet in the grand accounting of mass and energy, planets are small. Stars dominate the weight and the light. Planets dominate the potential for chemistry and biology. So when you hear a headline number for how many stars exist, try to see the shadow number that follows it. Multiply by a few to hint at how many planets may orbit those stars. Then imagine a fraction of those planets sitting in regions where liquid water could exist, and another fraction of those maintaining stable environments for long periods. The exact fractions are unknown. They could be tiny. Yet when you multiply anything non-zero by a star count that large, you enter a universe rich in possibilities. In the next part, we will turn back to the stars themselves and to the invisible partners that share the universe with them. The light we see from stars is only a small part of the total content of the cosmos. Dark matter and dark energy quietly shape the evolution of galaxies and the expansion of space. To understand what the star count truly means, we need to place it in that wider context and accept that even an exact number of stars would describe only a thin glowing layer on a much deeper reality. By now you have a rough sense of how many stars might live in a galaxy, and how many galaxies might live in the observable universe. It is tempting to think that once we have a handle on those numbers, we have grasped most of what exists. The bright parts feel like the main story. Yet when astronomers weighed the universe, they discovered something unsettling. The stars that dazzle us and the gas that feeds them are only a thin frosting on a much larger cake. The cosmos is dominated by things that do not shine at all. The first clues came from the motions of stars and galaxies. In a simple picture, stars near the center of a galaxy should orbit quickly, while stars farther out should move more slowly, the way planets in our solar system slow down with distance from the sun. When astronomers measured the orbital speeds of stars and gas in the outer parts of galaxies, they found something different. The outer regions did not slow down much. They kept circling at high speed, as if held by extra gravity from invisible mass spread throughout and beyond the visible disk. Similar puzzles showed up in galaxy clusters. Galaxies inside clusters move under the shared pull of the cluster's mass. In the middle of the 20th century, measurements suggested that the visible matter in those galaxies was nowhere near enough to keep them bound at the speeds they were moving. Something unseen had to be adding weight. Later, maps of hot gas in clusters and of how clusters bend the light of more distant galaxies confirmed the same story. There was more gravity present than visible matter could account for. The simplest explanation is that most of the mass in galaxies and clusters is in some unseen form that interacts very weakly with light. We call it dark matter. It does not glow. It does not absorb or scatter light in the usual way. Yet it feels gravity and produces gravity. In computer simulations of the universe, clouds of dark matter collapse first into halos. Ordinary gas then falls into those halos, cools and forms stars and galaxies inside them. In that picture, every galaxy lives in a much larger invisible cocoon of dark matter that extends far beyond its visible edge. On even larger scales, another mystery appears. When astronomers measured how fast the expansion of the universe was changing, They expected to find that gravity was slowing it down. Instead, they found the opposite. The expansion is speeding up. Distant galaxies are being carried away faster and faster by the stretching of space. To explain this, cosmologists introduced a new ingredient, a smooth form of energy that seems to be built into space itself. This is called dark energy, and it dominates the total energy budget of the universe today. Put these pieces together and the balance becomes striking. All the stars, planets, gas clouds, and dust that we can see make up only a small share of what exists. The normal matter we're used to, the kind made of atoms, accounts for only a modest slice of the total cosmic content. Most of the mass is in dark matter, and most of the energy is in dark energy. The glowing stars we have been trying to count are spectacular, but they are not the main component of the universe. They are like bright decorations on a mostly invisible structure. For our star counting exercise, this has two implications. First, the motions of stars and galaxies, shaped by dark matter and dark energy, are what allow us to infer the large-scale structure where stars live. Without dark matter, galaxies and clusters would not have formed the way they did. The cosmic web would look very different, and the number and distribution of stars would change. Second, when we estimate star numbers from galaxy motions, we always have to subtract out the dark matter contribution. Gravity tells us the total mass. To find the part in stars, we must peel off the invisible share. Gravitational lensing shows this beautifully. When light from a distant galaxy passes near a massive object on its way to us, the light path bends. In strong cases, one background galaxy can appear as multiple distorted images. In weaker cases, the shapes of many background galaxies are subtly sheared. By measuring these distortions across the sky, astronomers can map the distribution of mass, including dark matter, in foreground structures. These maps often reveal halos of mass that are much larger and heavier than the luminous galaxies alone. Stars trace only the densest peaks. Dark matter forms the broader hills and valleys. Even within a single galaxy, the luminous stars are only a minority by mass. In the Milky Way, the total mass in stars and gas is far less than the total mass implied by the rotation curve. Most of the galaxy's weight sits in an extended dark halo that reaches far beyond the visible disk. When we say the Milky Way has a certain number of stars, we are really describing the tiny fraction of its matter that has cooled and collapsed enough to ignite nuclear fusion, not the full reservoir of matter in which those stars swim. This changes the emotional tone of our star number as well. On one level, knowing that there are something like 10 to the power of 21 stars in the observable universe is awe-inspiring. On another level, realizing that all those stars account for only a small fraction of what is really out there is humbling in a different way. The most conspicuous things in the sky are not the most important from the point of view of mass and energy. Our eyes are tuned to a thin, flashy layer of reality. Dark matter and dark energy also remind us that our understanding is still incomplete. We can describe how they behave. We can measure their effects on galaxy motions, on the cosmic web, and on the expansion of the universe. But we do not yet know exactly what dark matter is made of, or why dark energy has the strength it does. These unknowns sit in the same equations that tell us how many stars live in a galaxy and how those stars move. The precision of our star counts is limited not only by faint light, but by mysteries in the underlying physics. At the same time, the existence of dark matter and dark energy does not make the star count meaningless. It places it in context. Stars are the main sources of light, heat, and heavy elements. They forge the atoms in our bodies and power the energy flows that make planets habitable. When we count stars, we are counting the engines of complexity in a universe otherwise dominated by dark, quiet components. The fact that these engines are rare by mass makes them all the more precious. In the next part, we will gather up the practical limits on our ability to count. Telescopes miss faint galaxies. Dust hides regions of star formation. Surveys favour bright systems and overlook the dim. We will examine how these biases and uncertainties stack up, and how wrong our headline number might be. Only then will we be ready to accept any final estimate of how many stars shine in the observable universe, and how big the error bars around that estimate really are. By now you might feel a quiet temptation. We have talked about star formation, galaxy surveys, the cosmic web, and the distance ladder. It is natural to want a clean final number. a neat line with a tidy figure that answers the question how many stars exist in the observable universe. But science rarely rewards that hunger with exactness. The real story is not just the number itself, it is the size of the fog around it. To be honest about how many stars there are, we have to ask an uncomfortable question. How wrong could we be? Start with the most basic limitation. Telescopes do not see everything. They see what is bright enough for long enough in the regions we happen to point at. Even the deepest images have a cutoff. Beyond a certain faintness, galaxies disappear into the background noise. Some are too small and diffuse to register at all. Others are hidden behind brighter objects along the line of sight. When astronomers count galaxies in a deep field, they're really counting the galaxies above a certain brightness threshold and then guessing how many lie below it. There is a subtle bias built into this. Bright galaxies are easier to detect than faint ones, so they are overrepresented in early surveys. In fields of view filled with both giants and dwarfs, the big luminous systems shout while the tiny low-surface brightness galaxies whisper. If you're not careful, you end up underestimating how many faint galaxies there are, and thus how many stars hide in them. Correcting for this requires models of the galaxy population and careful measurements of how detection probability falls off with brightness and size. Dust and gas add another layer. Inside our own galaxy, dust lanes hide stars from view in visible light. In other galaxies, especially edge-on spirals, thick bands of dust can darken large areas. In the distant universe, dust in intervening systems can dim and redden background galaxies. Observing in infrared wavelengths helps to pierce this veil, but no observation is perfectly transparent. Every patch of dust that blocks starlight makes the universe look a little emptier than it really is, unless we explicitly account for it. Then there is the problem of surface brightness. A galaxy can contain many stars and still be hard to detect if its light is spread over a large area. Think of a city at night viewed from space. A compact downtown glows strongly. A sprawling suburb with the same total number of lights will look dimmer because the light is spread out. In the same way, some galaxies are diffuse and low contrast against the sky. They are easy to miss even if their total light is significant. Over the last decade, surveys specifically hunting for low surface brightness galaxies have found many such ghosts, reminding us that old accounts were incomplete. Our position in the universe also introduces bias. We live in a particular kind of galaxy, in a modest group that sits on the edge of a larger structure. It is natural to build our intuition around galaxies like the Milky Way and Andromeda, yet they are not the only models nature uses. Dwarf galaxies are far more numerous by count, even if they contribute less to the total light. Giant ellipticals in rich clusters can hold staggering numbers of stars, yet make up only a small fraction of all galaxies. When we talk about a typical galaxy and its star count, we are smoothing over a wild range. On top of these observational limits sit modelling uncertainties. To turn galaxy light into stellar mass, astronomers adopt a stellar mass function that describes how many stars exist at each mass. There is good evidence for its general shape, but the exact proportions of low mass to high mass stars can vary from one environment to another. Change that function a little, and the inferred number of stars in a galaxy can shift noticeably. Low mass stars are faint yet numerous. If we have slightly misjudged their share, our star count swings. A similar issue arises with the ages of stellar populations. Young stars shine more brightly per unit mass than old stars. A galaxy with a recent burst of star formation will look bright for its mass. One that has been quiet for a long time will look dimmer. If our models misjudge the mix of young and old stars in distant galaxies, the link between light and mass bends. That again feeds into our estimate of how many stars those galaxies contain. Even the cosmic distance ladder contributes uncertainty. Different methods of measuring the expansion rate of the universe have produced slightly different answers. This ongoing tension in cosmology hints that there may be small cracks in our understanding of distances or in the physics that connects them. A small shift in the assumed size of the observable universe changes the volume over which we are counting galaxies. A slightly larger volume means more galaxies and more stars. A slightly smaller volume means fewer. Our headline star number floats on this sea of calibration. To cope with all these issues, astronomers do not rely on a single technique or a single survey. They combine deep, narrow images with wide, shallow ones. They observe in multiple wavelengths from ultraviolet to radio. They build simulations that mimic the growth of galaxies and compare them with real data. They refine the stellar mass function using nearby resolved galaxies where individual stars can be studied. They explore corrections for dust, surface brightness, and selection effects. Every few years, global estimates of galaxy and star numbers are revisited in the light of new data. The result is not hopeless confusion. It is a number with error bars. When you see a claim that the observable universe contains roughly 10 to the power of 21 stars, that figure is not plucked from thin air. It is the central value of a range, built from many lines of evidence. The true number might be somewhat lower or somewhat higher. Different teams might argue about whether the best figure is closer to 1 times 10 to the power of 21 or a few times that. But almost no one thinks it is only 10 to the power of 19 or as high as 10 to the power of 23. In other words, our ignorance has shape. We know that we are missing some galaxies and some stars, especially in the faint and diffuse tail of the population. We know that our models of stellar populations and dust introduce systematic uncertainties. We know that distance calibrations might shift slightly. Yet these factors stretch our estimate by factors of a few, not by factors of 1,000. For a question that spans the whole observable universe, that level of uncertainty is strangely precise. There is a philosophical twist here. Many people treat uncertainty as a flaw, a sign that science does not really know what is going on. In reality, carefully measured uncertainty is one of science's greatest strengths. It tells you not only what is likely true, but how far you can lean on that truth before it might break. When we say there are roughly this many stars in the observable universe, plus or minus some factor, we are not confessing defeat. We are reporting the honest limits of our tools. So when you picture the star number in your mind, imagine it written with a little halo of fuzz around it. The core of the number is bright and sharp. The edges blur. As telescopes improve and surveys deepen, that halo shrinks. New discoveries of faint galaxies or better models of stellar populations may nudge the central value up or down. The story is not a single announcement. It is a conversation between data and theory that has been going on for decades and will continue as long as anyone cares to look up. In the next part, we will walk right up to the boundary of what we can ever hope to know. All of our counts so far live inside the observable universe, the region from which light has had time to reach us. Beyond that horizon may lie more galaxies and more stars, perhaps many more. We will ask what it means to talk about the total number of stars in a universe that may extend far beyond our view, and whether the question how many stars exist has a meaningful answer at all. When people ask how many stars exist in the universe, they often imagine a complete answer, a final total, a number that covers everything. The trouble is that physics quietly limits what we can ever see. No matter how good our telescopes become, there is a hard boundary around our observations. We live inside what is called the observable universe, and the key word there is not universe. It is observable. Beyond that horizon, light has simply not had time to reach us yet. Whatever lies out there, its stars are not part of any count we can honestly make. To understand this boundary, think about light as a slow messenger. It is fast by human standards, but not instant. When the universe began, it was hot and dense. As it expanded and cooled, light finally became free to travel long distances. Since that moment, every ray of light has been racing outward in all directions. We can only ever see objects whose light has had enough time to arrive here since that release. Anything farther away than that distance is invisible to us in principle, not just in practice. This distance defines our observable universe. From Earth, or from any point near it, we can look in all directions and see out to roughly the same limit in terms of the time light has been travelling. Draw that limit as a sphere around us, and you get the region of space from which information carried by light has had time to reach us so far. The radius of that sphere is bigger than the simple age of the universe times the speed of light, because space itself has expanded while the light was on the way. The exact number is less important than the idea that there is a horizon. Beyond that horizon, the universe may continue. Most cosmologists think it does. The simplest models of cosmic expansion suggest that the universe is either extremely large or effectively infinite. The part we can see is then just one patch, one bubble in a far larger whole. There could be more filaments of the cosmic web out there, more clusters of galaxies, more stars and planets extending into the dark. Their light has not reached us yet, and in many cases never will, because the expansion of space is stretching them away faster than light can close the gap. This creates an odd distinction. When we say the observable universe contains a certain number of stars, we're talking about a well-defined volume. It is the region from which light has reached us by now. We can in principle count galaxies in that region, estimate their stellar masses, and arrive at a number with error bars. When we ask how many stars exist in the entire universe, we step into something more slippery. If the universe is infinite and roughly uniform on large scales, then the total number of stars may simply be infinite. That is not a countable total. It is more a statement about the structure of space. Even if the universe is finite but larger than the observable region, we run into limits. There might be a fixed total number of stars out there, but no signal can carry that information to us from beyond our horizon. No future telescope, no matter how advanced, can change that. We are inside a kind of cosmic bubble of knowledge. We can infer that more probably lies beyond, based on the smoothness of the cosmic background light and the large-scale patterns we do see, but we cannot map or tally it directly. It is tempting to imagine some clever workaround. Perhaps, you might think, subtle patterns in the cosmic microwave background could reveal the overall shape and size of the universe. In some scenarios, a finite but curved universe might leave repeating features on the sky if light had wrapped around it. Astronomers have looked for such signatures. So far, the patterns we observe are consistent with a universe that is very nearly flat and either extremely large or infinite. That does not give us a neat outer boundary to integrate over. It mostly tells us that if the whole has an edge, it lies far beyond our visible patch. There is also the fact that our observable universe shrinks in a practical sense as time goes on. Distant galaxies are carried away from us by the expansion of space. For some of them, there is a point beyond which any new light they emit will never reach us, because the space between us and them is stretching too fast. We may still see those galaxies for a long time from the light already on its way, but their future activity becomes disconnected from our future observations. The true shared region, where signals can go both ways, is smaller than the full observable volume. All of this might sound like it undermines the whole project of counting stars. If we will never know the full total, why bother? The answer is that the observable universe is large enough to be meaningful. The volume from which light has reached us already contains hundreds of billions of galaxies and something like 10 to the power of 21 stars. That is enough to study patterns, to test theories, and to understand the typical behavior of matter and light. It is not everything, but it is far from trivial. There is also a deep philosophical angle. Questions about total numbers in an infinite or unbounded universe may simply not have finite answers. Asking for the total number of stars in an infinite universe is like asking for the last integer. The concept sounds clear at first and then evaporates under scrutiny. In that situation, the better question is how many stars exist in a region of a given size, or what the average number density of stars is. Those are the kinds of questions our observations can answer, at least for our patch. So when someone casually asks how many stars are there in the universe, the most honest response has two layers. In the observable universe, within the horizon carved out by light since the Big Bang, there are roughly a certain number of stars, give or take a factor of a few. Beyond that, the total may be larger by an unknown factor, possibly infinitely larger, and no signal can bring us a more precise answer. The second part of that sentence is not a failure. It is a description of how space and time work. This split between what exists and what is observable can feel uncomfortable, but it is a useful kind of discomfort. It reminds us that the cosmos is not arranged for our convenience. We are not at the center of a neatly bounded sphere handed a complete inventory. We are creatures inside a finite horizon, making the best of the information that has arrived so far. The fact that we can even define and estimate the star count of our observable patch is already remarkable. In the next part, we will turn back from these outer limits and look inward at ourselves. We will ask what these enormous numbers, horizons, and uncertainties do to the human mind. Do they make us feel small, or connected, or something stranger? We will explore how different cultures and thinkers have reacted to the growing realization of how many stars there are and what it might mean to live under just one of them. You now carry in your head a set of numbers that no human being was born ready to handle. Hundreds of billions of stars in our galaxy. Hundreds of billions of galaxies in the observable universe. A total star count expressed as 10 raised to a power with more digits than anyone can feel. The universe did not evolve our minds to juggle such scales. Our ancestors needed to track seasons and faces, not galaxies. So when these numbers land in your thoughts, they do something unusual. They stretch, warp, and sometimes crack the way you feel about existence itself. For some people, the first reaction is a kind of vertigo. You picture yourself on a small rock circling an average star in an unremarkable arm of a spiral galaxy, which is itself only one island in a vast cosmic sea. Every number you learn seems to push you farther from the center of anything. The star count becomes a measure of how tiny you are. Out of 10 to the power of 21 suns, ours is just one. Out of all the planets that may orbit them, Earth is just another stone. It can feel like a slow erasing of human importance. This feeling is not new. Long before anyone knew the size of the universe, thinkers wrestled with the idea that Earth might not be special. When early astronomers suggested that the Sun, not Earth, sat at the center of the solar system, the shift was already emotionally heavy. Later, when the Milky Way stopped being the entire cosmos and became just one galaxy among many, some people felt that the rug had been pulled again. Each revision seemed to place humanity farther from the center and closer to the margins. Yet there is another way to read the same facts. Before telescopes, most cultures thought the stars visible to the naked eye were all there was. A few thousand points, perhaps jeweled into a solid dome. Many stories and systems of meaning were built on that small set. When you learn that there are more stars than grains of sand on all the beaches on Earth, you're not being pushed entirely out of the picture. You're being shown that the stage is far larger and more intricate than anyone suspected. The question becomes not why we are not at the center, but what it means to be aware at all on such a stage. Large numbers can numb us. When a number passes a certain size, the brain files it under the same label as many. 10,000 and 10 million and 10 billion can blur together unless you train your intuition. That numbness is dangerous when those numbers describe human lives or events. In the context of the cosmos, though, it can be strangely peaceful. Once you accept that the universe is not built to match your sense of scale, you can stop trying to force it to feel tidy. The star count becomes less a threat and more a quiet backdrop. Different traditions have tried to digest this in different ways. Some treat the vastness as evidence of a grand design. Others treat it as a sign that meaning must be made locally, not handed down from the size of the cosmos. In both cases, the star number plays a role. To those who see purpose written into the universe, the sheer abundance of stars and worlds hints at a generosity of creation. To those who see a natural unfolding of physics, the same abundance highlights the improbability of any specific chain of events, including our own, and thus the preciousness of each conscious moment. There is also a more practical psychological effect. When you hold in mind the scale of the observable universe, many everyday worries shrink a little. This is not to say that personal struggles are trivial. They are real and heavy inside a human life. But knowing that your anxieties unfold on a small wet planet circling a star in one galaxy, among hundreds of billions, can offer a strange kind of breathing room. You are part of a story that does not depend on you, which paradoxically can make your choices feel more genuinely your own. At the same time, cosmic scale can be misused as a blunt tool for cynicism. It is easy to say that nothing matters because the universe is so large and you are so small. That move confuses size with significance. Value is not measured in meters or in star counts. A melody does not become meaningless because the room around it is spacious. A thought does not lose its depth because the brain that holds it is tiny compared with a galaxy. The star number should challenge grandiose fantasies of human centrality, but it does not forbid meaning. It forces us to build meaning on firmer ground. There is another twist that often goes unnoticed. The same universe that makes you feel small also made the atoms in your body and the mind that can understand its scale. Stars forge heavy elements in their cores and scatter them in explosions and winds. Those elements cool into clouds that form new stars and planets. On at least one planet, those atoms learn to think and to ask how many stars there are. When you recite a number like 10 to the power of 21, you're hearing the universe talk about itself in one small region. From that angle, the star count becomes not a measure of your insignificance, but a measure of the universe's capacity for self-awareness. Out of the enormous number of stars and worlds, only a small fraction will host beings who can build telescopes, write equations, and share quiet documentaries about the cosmos. You are one of those beings, or at least you are listening to one. That does not make you the goal of cosmic evolution. It does mean that consciousness is one of the rare and remarkable things that stars and galaxies can do. History shows that each time our picture of the universe has expanded, humans have eventually adapted. At first there is shock or resistance. Then new stories, art and philosophies arise that fold the larger scale into how people live. The realization that there are many galaxies did not erase myth. It inspired new metaphors. Science fiction worlds filled with countless suns are one example. Deep spiritual reflections that invoke the night sky as a symbol of mystery are another. The raw star number becomes raw material for culture. There is a gentler practical effect as well. When you think about how many stars and planets exist, how long the universe has been making them, and how slowly it will fade, your sense of urgency can shift. Some choices are still urgent, some crises are still real. But other anxieties begin to look like noise. You may find it easier to focus on what actually improves life for yourself and others, rather than on chasing a feeling of cosmic importance. The star count does not tell you how to live, but it can clear away some illusions that make living harder. So what do these numbers do to the human mind? They can shrink it, if you let them, or they can stretch it. They can push you toward despair or toward a quieter, more grounded sense of wonder. The same facts support both reactions. The difference lies in how you hold them. If you stand under the night sky and see only your own smallness, you're reading one page of the story. If you also see that you are part of the universe that is finally learning to describe itself, and that your awareness is one small flame in a vast dark that mostly does not think at all, then the star count becomes a source of meaning, not its enemy. In the final part of this journey, we will gather everything we have learned. We will put a number, as honestly as we can, on how many stars shine in the observable universe right now. Then we will step back one last time and ask what it truly means that a species on one planet can write that number down, argue over its error bars, and still look up at the sky with the same ancient feeling of wonder. We have walked through local neighbourhoods of stars across the disk of the Milky Way, out into fields of distant galaxies, along the strands of the cosmic web, and all the way to the horizon of what we can see. Now it is time to do the thing this whole journey has been building toward. We will put a number, as honest as we can make it, on how many stars shine in the observable universe. Then we will ask what that number really means, and what it does not mean for creatures living under one ordinary star. Begin with the Milky Way. Using local star counts, the total light of the galaxy, and the gravity that holds it together, astronomers converge on a figure of a few 100 billion stars. One common estimate is around 200 to 400 billion. Remember that this is already a range and already built on models. Change the assumed mix of bright and faint stars, or the exact shape of the disk and halo, and the number shifts. Still, the order of magnitude is solid. Our galaxy is a city of a few 100 billion suns. Next, recall what the deep fields showed us. When telescopes like Hubble and James Webb stare at a tiny patch of sky, they see thousands of galaxies in that speck alone. Extrapolating from many such patches, corrected for faint and hidden systems, suggests that the observable universe holds on the order of a few 100 billion galaxies. Some estimates land near 200 billion, others are higher. The exact figure moves as surveys improve, but it is not 10 billion, and it is not 10 trillion. It sits comfortably in the hundreds of billions range. Not all galaxies are like the Milky Way. Many are smaller dwarfs with only a few million or a few billion stars. A smaller fraction are giants with up to 1 trillion stars or more. If you simply multiplied 200 billion Milky Way-sized galaxies by 200 billion stars each, you would overshoot. In practice, when astronomers fold in the full mix of galaxy sizes and types, they arrive at a lower average per galaxy than the Milky Way count. A rough middle ground is that the typical galaxy might contain something like a few tens of billions of stars. Now put the pieces together, hundreds of billions of galaxies, on average perhaps tens of billions of stars in each, with dwarfs pulling the average down and giants pushing it up. When you multiply those broad ranges, You land in a band of possibilities that cluster around a central value. Many careful studies suggest that the observable universe contains roughly 10 to the power of 21 stars. That is a 1 followed by 21 zeros. Said another way, it is about a sextillion stars. A few sextillion if you allow a factor of a few either way. Because we cannot write that many stars on a page, we use comparisons. One popular image is grains of sand. Estimates of all the grains of sand on all the beaches and deserts on Earth vary, but a common ballpark is around 10 to the power of 19 grains. If the observable universe really holds something like 10 to the power of 21 stars, then there are about 100 stars for every grain of sand on Earth. Another way to say it is that for every grain you pinch between your fingers, you might imagine a little cluster of 100 suns. Remember the fog around that number. Our telescopes miss faint galaxies and low surface brightness systems. Our models for stellar populations may underestimate or overestimate the share of small red dwarfs. Our distance ladder could shift slightly as new physics or better measurements refine it. Those corrections might raise the star count by a factor of 2 or 3, or lower it by a similar factor. So a cautious way to speak is to say that the observable universe likely contains somewhere between about a few times 10 to the power of 20 and a few times 10 to the power of 21 stars. A narrow band on a logarithmic scale, but still an enormous range in plain counting. Yet even that spread tells us something important. We are not wildly lost. We are not arguing about whether there are 1,000,000 times more stars or 1,000 times fewer. The uncertainties stretch the number by modest factors for such a huge question. That means our methods, from parallax and standard candles to galaxy surveys and simulations, are working together in a coherent way. The cosmos will no doubt surprise us with details, but it is unlikely to reveal that our basic grasp of the star census is completely mistaken. So what does it mean that there are roughly a sextillion stars in the observable universe? On one level, it is just a description. It says that, averaged over the vast volume we can see, matter has gathered into that many long-lived nuclear furnaces. It encapsulates the history of star formation, the clumping of matter into the cosmic web, and the balance between gravity and expansion. On another level, it is a hint about the number of planetary systems, the number of potential chemical laboratories, the number of skies under which stories might unfold. It also means something personal. That figure 10 to the power of 21 does not live in the universe by itself. It lives in human minds. It was built slowly, over centuries, by people who ground lenses, pointed telescopes, measured tiny shifts in starlight, and compared notes across generations. It sits at the end of a chain of reasoning that links ancient star catalogues to space telescopes and supercomputer simulations. When you hear it, you're touching the tip of that long effort. You're letting the universe, filtered through human curiosity, describe its own structure. There is a tempting final question. If the observable universe holds that many stars, and there may be much more universe beyond our horizon, does the true total matter? In a strict mathematical sense, perhaps not. If the universe is infinite and roughly uniform, the total number of stars simply diverges. It becomes a question with no finite answer. The more meaningful quantities are local. How many stars per unit volume? How many stars in the region where light can reach us? Those are questions our instruments can address, and they already yield awe. So let us accept this. In the region of space from which light has had time to reach us, a region about as large as it is physically meaningful for us to talk about, there are on the order of a sextillion stars. Whatever lies beyond that horizon will remain guesswork. The number we have is not perfect, but it is real in the sense that it is grounded in observation and calculation rather than wishful thinking. It will be refined, nudged, and polished in future decades, yet it will not suddenly shrink to a comfortable size. When you go outside at night after this, you will still see only a few hundred stars from a typical location, a few thousand under the best dark skies. The Milky Way will still look like a pale band. No new sense of scale will change how the air feels on your skin or how the cool dark wraps around you. The difference is that somewhere in your mind, behind those pinpoints, there will be a quiet awareness. The awareness that those few dots are the barest hint of a population so large that even our best words struggle to hold it. In the end, perhaps the number itself is less important than what it invites you to do. To look up more often, to question your own intuitions about size and importance. to see your life not as the centre of all things, but as one brief and astonishing pattern in a universe that is finally learning to count itself. Under one star, on one world, a mind like yours is capable of carrying the idea of a sextillion. That may be the most remarkable fact of all.